For this part, we're going to be talking about the molecular geometry and the shape of the molecules that are formed. It's really important to know what the geometry and shape of the molecules are so that you could help predict the properties of that molecule. So if we look here, we have a linear shape or linear geometry, and the shape, of course, is just a line. It might be two elements together, so just one or two, or it could be three. If it's only two elements, it's automatically a linear shape because there's no other geometry that can be made. But if you have three elements, you're going to have a linear shape as well if you have two pairs of bonding electrons on the central atom. So the pairs of bonding electrons and pairs of non-bonding electrons, those all pertain to the atom that's here in the center. So the center atom is what these bonding pairs refer to. So all of these have to deal with the central atom. With tetrahedral shape, you have a central atom with four different objects attached to it, four different elements. So you're always going to have four bonded pairs of electrons and zero non-bonded pairs in a tetrahedral. In a trigonal pyramidal, you're going to have your central atom here, but only three non-bonding or three atoms that are bonded to that central atom. You're also going to have one non-bonding electron pair. That non-bonding electron pair always takes up more space. So it's going to push the other bonded pairs to the central atom closer together. For the bent geometry, you have two different variations of the shape. You can have something like water right here in number one, where you have a central atom, you have two atoms bonded to it, and two non-bonding pair. Or you can have something like boron, if you remember. Boron can only have six. It doesn't meet the octet rule. It can only hold six electrons total. And so this would be something that you could do with boron, where you have two bonded pair, but only one non-bonding pair of electrons. And then trigonal planar is something that boron does as well, because if all three of its bonding sites are filled and it has three bonding pair of electrons, it's going to have the trigonal planar. So it's going to be basically flat like this, where everything's all in the same plane. That's where that planar comes from. We need to work on drawing Lewis structures in order to determine the molecular geometry of the objects. Now, in order to draw the Lewis structures, you're going to have to be able to look at the periodic table. Look at the periodic table and find the element, and then based off the group, tell me how many valence electrons it has, and show those on your document as you're drawing. So chlorine is in group 17. That means that there are 7 valence electrons. So if I were to draw chlorine, I do Cl and Cl. I'm going to just put them both there. And I know that chlorine has 7 valence electrons. I know that I have 2 of them. So I need a total of 14 electrons on my drawing. And it's nice to know how many you need because whenever you're erasing and rearranging, sometimes we forget to add one back or we add too many because we forgot to erase one. So it's nice to know at the beginning how many you should have. So if I'm going to add 7 valence electrons for each chlorine atom, I have 1, 2, 3, 4, 5, 6, 7. Now I'm going to have 1, 2, 3, 4, 5, 6, 7. My first step is to make sure all of my electrons are paired. Well, I have 3 here in the center, but a lone one here on the end. So I am going to erase that one and put this right here. So now that I've rearranged, I'm going to check and see if I have 8 surrounding each element. So I have 2, 4, 6, 8 around this chlorine on the left. So that's all good. On the right, I have 2, 4, 6, 8. So I have all 8 there. Based off the geometry, if I were asked what geometry this is, I know that it's a linear geometry because I only have 2 elements. There's no other shape that it can make. If we were to do all of our diatomic molecules and determine their shapes, what shape do all diatomic molecules have? They all have a linear shape because it's only 2 elements. So now we can ask ourselves the question, would chlorine be polar or nonpolar? Well, we know that all diatomic molecules are nonpolar because the electronegativity difference is 0. If we wanted to check, we would go to our chart from the previous class and we'd find chlorine here, which is 3.0. And I could write that as to show the math. 3.0 minus 3.0 equals 0. Remember, anything between 0 and 0.5 is nonpolar. All diatomic molecules have the same polarity because it's value minus its value. That will always be 0. All diatomic molecules share their electrons equally. Now, what about molecules that have more than 2 atoms? It's not going to be as easy. For molecules with more than 2 atoms, you're going to need to assume that nature likes to be symmetrical. And therefore, one of the atoms is going to be the center of the molecule. There is an exception, though, for hydrogen. Remember, hydrogen only has the S sublevel. The S sublevel can only hold 2 electrons. So hydrogen can't have more than 2 electrons. If it can't hold more than 2 electrons, it can't be the center because if you made it the center, it would have to hold at least 4, and that can't happen. So hydrogen will never be the center of the molecule. You would go to the next molecule over in order to draw the molecule. Now, if you're not sure what the central atom is, a good rule is that the atoms with the highest electronegativity are going to be the center of the molecule. It's not always the case, but it's a good rule of thumb. The other atoms are then symmetrically placed around the central atom. So if we're going to practice, what is the correct Lewis structure for carbon dioxide? It's a good idea to draw your Lewis structures and then double check for the answers. So I want you to first answer these questions and then come back and check your answers. So what's the correct Lewis structure for carbon dioxide? We have our first element. It's not hydrogen, so it can go in our center. If you look on the periodic table, you'll see that carbon has 4 valence electrons. So I'm going to draw 1, 2, 3, 4 here. Now, I put on my oxygens. I'm going to put 1 oxygen here and 1 oxygen on the other side. Because remember, nature tends to make symmetrical things. Each oxygen comes with 6 valence electrons because it is in group 16. So I'm going to 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now, I know that electrons need to be paired up. I have all my electrons on there. I'm going to move this one here to the bottom of the right oxygen and pair it that way. I have 1 lone electron on top of carbon and 1 lone electron in the center between carbon and the left oxygen. I'm just going to remove that. I didn't mean to remove the carbon as well. And I'm going to put that erased electron right there. Now I'm going to pair up these electrons on the left oxygen. And then I'm going to check and see if I have the octet rule satisfied for all my elements. So if I look here on the left oxygen, I have 2, 4, 6. That one's not okay. Carbon has 2, 4, 6. That one's not okay. This oxygen on the right has 2, 4, 6, 8. So the only element so far that has the octet rule satisfied is the oxygen on the right. I need to get every single element in this molecule satisfied by the octet rule. So how can I get this oxygen to have 8? I can't take anything from it, but I need to make sure that this has 8. I can share more than 2 pair of electrons. So I'm going to take these electrons off the top of carbon, and I'm not going to take it away from them, but I'm going to share them with oxygen. So now, if I looked at this, I have 2, 4, plus 4 is 8. So this oxygen is good right here. Let's look at this carbon. I have 4 and 2. That's a total of 6. I don't have the octet rule satisfied. So I'm going to look and say, well, am I symmetrical? I'm not symmetrical because if you look at how these electrons are and how these electrons are, I couldn't fold it in half and have them line up exactly because the electrons aren't arranged symmetrically. So I'm going to try to arrange them symmetrically by removing these bottom electrons and moving them to the center here. After I've done that, I'm going to double check. I know this one here still has 8 because I didn't touch anything there. This carbon now has 4 plus 4, which is 8. And this oxygen has 2, 4 plus 4 is 8. So we know that the answer is going to be A with because each oxygen has 2 lone pairs. Now with number 2, it says which of the following molecules has lone pair on the central atom in its Lewis structure? That means we have to draw each structure. So CH4, C is going to be my central atom. It's in group 14, which means it has 4 valence electrons that it comes. There are 4 hydrogens. Each hydrogen comes with 1 valence electron. Now, this doesn't have any lone pair of electrons, so I know the answer is not A. Let's look at B. B is ammonia, NH3. So nitrogen's going to be my first element, my central element. And if I look at the periodic table, I see that nitrogen is in group 15. That means that I have 5 valence electrons. So let's draw those. 1, 2, 3, 4, 5. Now, hydrogen comes with its own valence electron. 1, and we have 3 hydrogens. 2, 3. Let's double check, make sure that we have our octet rule satisfied. Each hydrogen has 2, which is the max that it can hold, so it's happy. And nitrogen has 2, 4, 6, 8, so it's happy. And what does it also have at the top? A lone pair. So the answer is B. Now let's look at number 3. Number 3 says, what's the total number of electrons represented in the Lewis structure of nitrogen gas? Well, nitrogen, we know, has 5 valence electrons because it's in group 15, which means it has 5 valence electrons. There are 2 nitrogens here. So 5 times 2 gives me 10. If I drew N2 as a Lewis dot diagram or dot structure, I would need to make sure it had 10 valence electrons, which is A. Now, the VSEPR theory is an important theory in terms of molecular geometry. It stands for valence shell electron pair repulsion. And this just states that the electron pairs around a central atom tend to be as far apart as possible from each other. So if we drew the structure for methane, which is CH4, and which we did on the previous page, number 2, so I'm just going to draw it here. And we wanted to determine the structure, we could do that. We would look for how many pairs of electrons are around the central atom. So we could see each line represents the two dots. Remember, you could either do it like this, or you could do it with the lines. Either way is accepted. So either way is good. So we'd look at how many pair of electrons there are. So there's 1, 2, 3, 4 pair of electrons here. And then we would go to our chart and look to see what this chart here. There are 4 pair of electrons. There are 0 pairs of non-bonding electrons. So what is the geometry? It would be tetrahedral. What is the shape? It would be this shape here. And it would have 109.5 degrees between each hydrogen because it's trying to maximize the space equally between each hydrogen. Now, how can these pairs of electrons arrange themselves around an atom so that they're as far away from possible? It's like this, 109.5 degrees, 109.5 degrees, 109.5 degrees. Tetrahedral, or any geometry actually, spreads out the bonding atoms or electron pairs, trying to spread it out so that way the electrons aren't on top of each other. So they spread out to be symmetrical. Now, building on what we did last class, would methane be a polar or nonpolar molecule? Let's look. If we have CH, H, 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 we need to look at each individual bond. So we could look at our chart from before, right here, and find carbon, which is 2.5, and find hydrogen, which is 2.1. And then do our bond electronegativity calculation. So we'd say 2.5, oops, minus 2.1, and that would give us 0.4, which is nonpolar. So this bond is nonpolar, this bond is nonpolar, this bond is nonpolar, and this bond is nonpolar. Because it's symmetrical and all of these bonds are made with the same atom, this is a nonpolar molecule. What if instead, though, we had this molecule? We had carbon. That's kind of hard to see, so let's get a different color. So we have carbon here as the center atom. And then hydrogen, hydrogen, hydrogen. And then let's make that fluorine. So if we did this, this one's 0.4, this one's 0.4, this bond's 0.4, but this bond instead would be 4 minus 2.5, which is 1.5, which is polar covalent. So if this bond is polar covalent, it means that this molecule itself is polar. So it's important to know polarity of molecules because we will know how they'll behave. In fabrics like wick, like the sweat wicking fabrics that you like to wear, I like to wear them whenever you're exercising. It's important to know the molecules within the fabrics because that polarity in the fabric is what is able to wick the sweat away from your body. So knowing that property of the molecule can help us apply its use. Now, what if we have another molecule? What if it's all fluorines? Then we have 1.5, 1.5, 1.5, and 1.5. Because this is all the bonds are polar, you might say, well, that is easy. That's a polar molecule. That's not necessarily the case because you have the electrons being pulled this way, the electrons being pulled that way by fluorine, the electrons being pulled that way by fluorine, and the electrons being pulled that way by fluorine. When you have equal but opposite directions, the forces cancel each other out, which makes the molecule, even though it has polar bonds, the molecule itself is nonpolar. It's a little tricky. Now, to determine, we talked about methane being polar or nonpolar, we'd have to look at the bonds and the shape of the molecule and draw the dipole. And just as a little review, the dipole is the result of the electrons being shared unequally. And the larger the electronegativity value of the atom, the greater its attraction for a shared pair of electrons in a covalent bond. When we draw, it's important to remember, when we draw Lewis structures that have non-bonding pair of electrons, like with our ammonia, when you draw something like this that has a non-bonding pair at the top, these non-bonding pairs actually take up more space. And that's why the drawing in the chart was like this, like a little balloon on top, because it's showing the space that that non-bonding pair takes up. And you will always result in a polar molecule if you have non-bonding pairs of electrons. And the VSEPR model works for multiple bonds if we assume that if we have a multiple bond, that it acts as a single pair of electrons. So we could have carbon monoxide here. And if we just assume that this acts as a single bond, even though it's a triple bond, we'd say, oh, it's okay. It acts as one single bond, so this would still have a linear shape. The thing is, though, a triple bond has a shorter length than does a single bond. A double bond between two atoms is always shorter than a single bond between the same two atoms. So you could have your carbon and oxygen, which is a single bond, but if you have carbon and oxygen as a double bond, it's going to be shorter. And the same goes with a triple bond. The more electrons you have in a bond, the more tightly the two atoms are held together. Think about putting nails and nailing a board down. Do you just put one and walk away? If it's a large board, probably not. You want to have at least two and sometimes more on each end to try to make sure that it's secure. And single bonds and double bonds and triple bonds, it's the same thing. You hold it down more tightly if you have more electrons there. So here we have sulfur dioxide. Let's draw sulfur dioxide. Sulfur can go in the middle, and it's in group 16. So I'm going to draw my 6 valence electrons. 1, 2, 3, 4, 5, 6. Then I have 2 oxygens, that can go on either side. So 1 oxygen, 2 oxygen. Oxygen is also in group 16. So I'm going to add those 6 electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I have all my electrons on there. Now I need to pair up my single electrons. So I'm going to move this one from the center, and I'm going to put it here on the bottom. Pair it with that one. I'm going to move this one, this lone one there, and pair it with the one here on the bottom of sulfur. Then I'm going to take this one on the bottom of oxygen and put it here. Oh. There we go. With this oxygen. Now I'm going to determine if I have the correct number, if everybody has the octet rule satisfied. This oxygen on the left has 2, 4, 6. It does not. It's not satisfied by the octet rule. It's not happy. Things will continue to react until the octet rule is reached. So the correct Lewis structure must have the octet rule satisfied for each element. Sulfur has 2, 4, 6, 8. It's good. The oxygen on the right has 2, 4, 6, 8. It's good. So the only one that isn't good is the oxygen on the left. In order to do that, I need to give this oxygen 2 more without taking away from sulfur. I can do that by sharing 2 electrons. So I'm going to take those top 2 electrons and I'm going to move them into the center. So now let's look. I have 2, 4, plus 4 is 8. I have 4 plus 2 plus 2, which is 8. And then I have 2, 4, 6, 8, which is good. Now I realize this isn't exactly symmetrical, and that happens sometimes. If we put these two, and I realized actually, yeah, if we moved some to make it more symmetrical, we would have more than 8 electrons around one of the atoms. And so we're not going to do that. This is what it is. And we realize that there's actually something called a resonance structure. So there's something in between, because whenever we did experiments, or scientists did experiments, you can see that, wait, this would be a shorter bond than this one, but actual experiments show that those bonds are closer in length to each other. So what they realized is they said it must be like a hybrid where you have the double bond here, it's more like 1.5 bonds on each side. So something happens within the molecule to make it more like 1.5 bonds. But if you're ever told to draw it, you're going to draw it so it looks like this. And it's like 1.5 bonds because they're two hybrid bonds. So then if I wanted to know what the shape of this is, remember I treat this as a single element. And it's not going to be linear, or as a single bond. It's not going to be linear because I have this lone pair of electrons. I know this one's a tricky one. So if I go back to that chart here, right here, it's not going to be like this. It's actually going to be a bent pair because that, a bent shape because that pair of electrons is going to, this pair of electrons here at the bottom is going to cause it to bend a little bit. So if I drew it like this here, remember this is going to take up more space. So then you'd have the oxygen more like this. So this is going to be a bent shape because this lone pair of electrons is going to prevent it from being linear. And if we have a lone pair of electrons, is this polar or nonpolar? It's going to be polar because anytime you have a lone pair of electrons, that indicates polarity. Almost done. Now, what is the predicted shape of a molecule that has 4 bonding pairs and no lone pairs on the central atom? I want you to try these questions on your own and then come back once you've answered them to see if you've gotten it correct. So what's the predicted shape of a molecule with 4 bonding pairs and no lone pairs on the central atom? You're going to use this chart to help. So there are 4 bonding pairs right here. No lone pair of electrons. So this, A, would be a tetrahedral. Which is D. Which molecule has a bent molecular geometry? In order to answer this, you'd have to draw all of the Lewis dot structures. Carbon dioxide looks like this. That one's not bent. It's completely symmetrical, so this would be linear. So we know it's not that. We did CH4 before. There are no lone pairs of electrons, 4 bonding sites. So this one is actually tetrahedral. Let's do water. Water, the oxygen goes in the center. We have our hydrogen, and then we have 2 pair of unbonded electrons. That one would give us the bent shape. So if you look here, it's right here. 2 pairs of bonded electrons, 2 pairs of non-bonded electrons. That gives us the bent shape. Now, which of the following correctly matches a molecule with its molecular geometry? We already know that CH4 is tetrahedral. We know that H2O is bent. We know from the previous slide that SO2 is bent. So this one, C, would be the correct one. But you should always check all answers. BF3 tetrahedral, BF3 looks like this. 3 bonded pair of electrons, no unbonded pair of electrons. This is your trigonal planar right here. So that one is not correct. The correct answer is C. Yeah, always check. If you say, oh, I know it's this answer, always double check. Okay. Now, why does polarity matter? I talked about one application with the moisture wicking fabric. It works by mixing polar and nonpolar fabrics. The polar fabrics or the nonpolar fabrics push the moisture away from you. The polar absorbs the water. So by interweaving the fabric, you have the ability to absorb the moisture from your body, and then the nonpolar fabric pushes it out away from you. There are other uses as well, but that is one common one that you use these polar and nonpolar materials regularly and don't even realize how important they are to you. These concepts are. Now, the hydrophilic, which is a polar molecule, attracts the water, and the hydrophobic, which is the nonpolar molecules, repel the water. And so by repelling the water, it pulls the moisture away from your body, and you don't have to worry about wearing a sopping wet cotton t-shirt because you have that moisture wicking fabric. All right. That's it. I hope you guys have a wonderful rest of your week.